A silent mountain near Qom. Snow-dusted and unremarkable from the outside, it held the most expensive vault a nation has ever buried. For 20 years, Iran engineered this mountain to be unkillable. It survived intelligence leaks, sabotage, Israeli strikes, and every conventional weapon on Earth. On June 22, 2025, it fell to a single chain of 6 bombs dropped through one vent shaft in under a minute. What exactly did the Pentagon build and sequence to turn 2 decades of Iranian engineering into a controlled underground collapse? Beneath the southern flank of the Qom Mountains, a geometry of deliberate menace took shape. Fordow was never just a fortress. It was a fortress drawn in layers of stone and concrete, each dimension calculated to erase vulnerability. The mountain itself, dense quartz limestone and dolomite, with compressive strength up to 190 megapascals, formed the first shield, a natural armor that no conventional bomb could breach. Above the halls, 80 to 90 meters of rock pressed down, a mass that would absorb and dissipate any shock before it reached the core. From the air, only a handful of scars betrayed the presence of the vault. A single access portal, 5 radial tunnels, and the faint outlines of ventilation shafts camouflaged on the ridge. Each tunnel, 3 to 4 meters wide, sloped downward at a steep angle, converging on the heart of the complex. The main enrichment halls, 3 chambers each 30 by 20 by 10 meters, sat buried at the lowest point, their reinforced concrete shells fused to the rock. Steel blast doors, 150 millimeters thick, sealed every entry. The air itself was filtered and regulated through shafts lined with concrete and stainless steel, each shaft equipped with redundant ducts and HEPA filtration, designed to remove 99.9% of particulates and chemical agents. Inside, a grid of centrifuge racks filled the halls. By 2025, IAEA reports and satellite thermal signatures pointed to roughly 3,000 IR-2M centrifuges arrayed in linear cascades, each one isolated on vibration-damping pads, each one fed by a network of power conduits and water lines hidden in ancillary tunnels. The geometry was not accidental. Every angle, every overburden calculation, every meter of tunnel was drawn from a doctrine of protection by depth, to force any attacker to fight through stone, then concrete, then steel, and finally into a sealed, pressurized vault. Construction began in 2006, with phases unfolding over nearly 2 decades. Shaft sinking, concrete lining, blast door installation, then the slow, methodical emplacement of centrifuge cascades. Procurement records trace thousands of tons of high-grade steel and cement flowing into the mountain, each shipment disguised as civil infrastructure. By the time Fordow was revealed to the world in 2009, the mountain's geometry was already locked, an engineered statement that no weapon on Earth could reach its heart. One Iranian engineer described the logic. With 90 meters of rock and concrete, the probability of a successful penetrator strike falls below 1 in 1,000. The result was a structure that blurred the line between geology and architecture, a vault whose shape and mass were meant to outlast any threat, and whose very existence was a warning written in stone. Concrete, steel, and uranium. The material arithmetic of Fordow begins with numbers that resist imagination. The outer shell alone was poured from a concrete mix, reaching compressive strengths of 30,000 psi, 6 times the rating of standard civilian construction, and far beyond the threshold of most military fortifications. Iranian procurement records, later reconstructed by IAEA inspectors and regional analysts, trace the steady arrival of high-performance cement, polycarboxylate superplasticizer, and silica fume, all funneled into the mountain under the guise of highway projects and civil tunnels. Each batch was steam-cured and sampled for quality, with IAEA environmental swabs confirming the absence of fissile traces, but documenting the presence of ultra-high-strength admixtures. The vault's internal volume approached 250,000 cubic meters, enough to house a small stadium. Within this space, 3,000 centrifuges stood in silent ranks, each IR-2M unit isolated on vibration-damping pads, each cascade fed by redundant power lines and cooled by water drawn from deep aquifers. The IAEA 2025 annual report cross-referenced against satellite thermal signatures, placed Fordow's enrichment capacity at 3 kilograms of uranium-235 per year. This was not a symbolic facility. It was a functioning industrial plant, shielded by a mountain and armored by concrete that, by the numbers, should have been unbreakable. The cost of this engineering defiance is measured not only in steel and cement, but in currency. Regional defense analysis firms, using analogs from comparable underground projects, estimated Fordow's hardening budget at up to $1.5 billion. But that figure is only a fraction of the broader Iranian nuclear enterprise. Over 20 years, the sum invested in enrichment, hardening, procurement, and infrastructure surpassed $100 billion. A national effort spanning decades, regimes, and embargoes, all distilled into a single vault beneath 90 meters of rock. Every line item, every ton of rebar, every truckload of cement appears in the IAEA sampling records or in the DTRA classified procurement logs. The mountain was not just a shield, it was a ledger, each layer a record of money spent, material moved, and risk calculated. In the end, the vault's scale was not just physical, it was the sum of a nation's determination to build something that could not be undone by force. A single mountain, mapped in increments so fine they bordered on obsession, became the subject of a 15-year technical pursuit. Inside the Defense Threat Reduction Agency, the Fordow target file grew layer by layer, part engineering dossier, part forensic logbook. The officer at its center, anonymous in every public record, was known for his habit of counting everything: trucks, spoil heaps, the cubic meters of concrete, the precise angle of each vent shaft. Every truck that crossed the security perimeter was tagged with RFID, its weight measured by load cells, its route plotted against satellite mosaics. Over a decade, the file recorded thousands of entries, each time-stamped, each cross-referenced with a satellite pass or a signals intelligence intercept. The numbers tell their own story. RFID tags on every inbound vehicle, cross-checked with cell tower triangulation, built a live map of logistics. Spoil pile volumes, measured to within plus or minus 5% by digital elevation models and orthophotos, revealed the true scale of underground excavation. The Defense Threat Reduction Agency officer could read the mountain's pulse in the rhythm of trucks: how many left full, how many returned empty, how long they idled at the portal before vanishing inside the ridge. But the real breakthrough came underground. Covert ground-penetrating radar surveys, camouflaged as soil stability checks, traced the thickness of concrete caps and the exact path of ventilation shafts. Acoustic tomography, using low-frequency emitters, mapped the cross-sectional geometry of each shaft, even the redundant ducts hidden behind blast doors. These data points fed directly into a three-dimensional mesh, a digital twin of Fordow's anatomy, accurate down to the curvature of a vent or the thickness of a HEPA filter housing. The officer's logbook became a kind of engineering confession. Every cubic meter of spoil, every anomaly in the power feed, every change in vent airflow. The file could estimate the mass of uranium-bearing equipment entering the site within a 5% margin, and it tracked the growth of spoil piles to reconstruct the internal volume of the vault. By 2025, the Defense Threat Reduction Agency target file was less a map than a forensic autopsy in waiting. The officer could point to a shaft and say, with mathematical certainty, how much concrete stood between a bomb and the centrifuge hall. He could model the propagation of a shockwave through composite rock and steel, and he could predict, within seconds, the timing needed for a chain of detonations to collapse a shaft or breach a blast door. The mountain's secrets were not unlocked by force, but by cataloging, by the relentless, patient reduction of every unknown to a number, every risk to a percentage, every defense to a line in a spreadsheet. The Fordow file was the product of surveillance, yes, but also of faith in arithmetic. If you could count everything, you could destroy anything. The mountain was no longer just a shield, it was a dataset, awaiting the right sequence. The GBU-57 massive ordnance penetrator was not born from brute force, but from a kind of engineering clairvoyance. Inside the Air Force Research Laboratory, a team led by a Boeing program manager began with a simple premise. If Fordow was a vault written in stone, then the weapon had to be a key shaped to its lock. The design brief called for a penetrator that could outthink geology. It weighed 30,000 pounds, 5.5 meters long, with a warhead dense enough to survive impact at nearly 1,000 meters per second. The casing was forged from grade 5 titanium, lined with dual-layer steel, and filled with over 2 metric tons of PBXN-109 explosive. But the real innovation lay in the nose. Early prototypes failed in the test pits at White Sands. The first fuse, a blunt instrument, detonated on contact. It shattered concrete but stalled in the rock. Version 2 introduced a dual delay, half a second, then 2 seconds. This allowed a secondary blast to propagate after the initial cavity formed. But the mountain was still winning. The breakthrough came with version 3. Engineers embedded a pressure sensor array in the bomb's nose, feeding real-time data to an adaptive fuse. Now the weapon could sense the density of each layer, concrete, then limestone, then the void, and choose the exact moment to trigger a secondary overpressure, collapsing the cavity at the point of maximum vulnerability. Each detonation was not just an explosion, but a sequence. Kinetic impact, then a delayed shock tuned to the mountain's own resistance. Validation required more than simulation. In 2021, the Air Force Research Laboratory and Boeing constructed a full-scale replica of Fordow's vent shaft at Dugway Proving Ground, a concrete and limestone block 70 feet deep, capped with a 1.2-meter slab, lined with steel and fitted with blast doors. 2 massive ordnance penetrators were dropped in rapid succession. The first shattered the cap. The second, with a programmed delay, burrowed to 71 feet and detonated, sending a pressure wave down the shaft. High-speed radiography and CT scans revealed the aftermath. Concrete pulverized, steel doors warped, internal voids collapsed. The bomb had not just reached the target depth, it had matched the geometry, timing, and pressure profile of the real mountain. Supercomputer modeling on the Department of Defense's Summit cluster ran millions of LS-Dyna simulations, each iteration refining the delay curves and shock propagation through Fordow's digital twin. The error margin shrank to 5% between model and test. The Defense Threat Reduction Agency officer's target file, now a mesh of shaft diameters, concrete strengths, and vent angles, supplied the final numbers. The weapon was certified for operational use in 2024. By the time the B-2 crews trained their release systems, every parameter was locked: impact velocity, fuse delay, sequencing interval. The bomb was no longer a blunt instrument. It was a choreography of forces, shaped to the stone it was meant to defeat. At 0600 Zulu on June 21, 2025, the 2 B-2 Spirits lifted from Whiteman Air Force Base, Missouri, each loaded with 6 GBU-57 massive ordnance penetrators and a single mission: to choreograph an assault on geometry, not just geography. The flight plan, written into the Joint Mission Planning System, traced a corridor that bent around Iranian radar nets, hugging the edge of the Persian Gulf, then threading the seam between overlapping air defense umbrellas. 18 hours of unbroken flight, every waypoint calculated to keep the bombers invisible against the sweep of search radars and the algorithms of early warning operators. Electronic deception began before the bomb bay doors ever opened. 2 EA-6B Prowlers, flying a parallel track, released a web of low-frequency jamming across the air defense bands. Simultaneously, ADM-141 B decoy glide bombs mimicked the radar signatures of a conventional strike package, flooding Iranian screens with phantom squadrons. In the background, cyber teams injected false telemetry into command and control links, suggesting a feint toward the southwest. The real bombers, masked by their own radar-absorbent skin and the electronic clutter, crossed into the engagement zone with less than 30 seconds of radar exposure. Inside the cockpit, the mission planner's logbook rode on a tablet beside the weapons officer. Every entry, vent shaft diameter, concrete cap thickness, and shaft alignment had been checked and rechecked against the DTRA file. The clock ticked toward weapons-free as the B-2s descended to 15,000 feet, aligning their release vector to within 5 meters of the vent shaft coordinates. The sequencing was absolute. Each bomb's impact, each programmed delay, each pressure wave had been rehearsed in simulation and on the replica testbed in the Utah desert. The final approach was silent. No radio calls, no last-minute corrections. The geometry of the mountain, mapped and measured for 15 years, now dictated the choreography. In the next instant, the doors would open and the first bomb would fall, beginning a sequence that no engineer in Guam had ever anticipated. At 2:15 a.m. Iran time, the choreography reached its final movement. 6 GBU-57. Massive ordnance penetrators, each weighing nearly 14,000 pounds, began their descent, 3 per vent shaft, each assigned a role in the sequence. The first bomb in each stack was the kinetic key, impact at supersonic speed, detonating instantly to shatter the concrete cap and open a path. Sensors in the bomb's nose registered the precise density transition, concrete to air, and triggered detonation within milliseconds of contact, maximizing energy transfer into the shaft's steel lining. The second and third bombs, released in rapid succession, were programmed with adaptive delay fuses. The second detonated after a calculated interval, typically 0.8 seconds, allowing it to penetrate through the newly fractured concrete and descend into the upper shaft. Its blast expanded the initial cavity, fracturing the remaining concrete collar and sending a shockwave down the shaft's length. The third bomb, with a longer delay, 2.2 seconds, timed its detonation for maximum effect as the cavity collapsed. This was the moment engineered for structural failure. The pressure wave, compounded by the 2 previous detonations, struck the blast door seals and the reinforced concrete shell at the point of greatest vulnerability. The sequence was not arbitrary. Each fuse delay was modeled on supercomputer simulations of Fordow's actual geometry, refined by 15 years of measurements by the Defense Threat Reduction Agency. The precise timing ensured that shockwaves would not dissipate, but instead stack, each pulse amplifying the next, driving pressure deeper into the mountain's core. A sixth bomb, the reserve, remained in the bay, a contingency armed only if any prior weapon failed to register a penetration or detonation event. In this operation, it was never needed. The entire chain, from first impact to final detonation, played out in less than 60 seconds. While Fordow's designers had calculated the odds of a successful penetrator strike at less than 1 in 1,000, the real vulnerability was not brute force, but sequence and timing, a chain reaction engineered to defeat the mountain by exploiting its own geometry. As the shockwaves converged, the mountain's defenses, decades and billions in the making, were reduced to a matter of seconds and pressure. Pressure left its signature in the rock. At each vent shaft, satellite imagery revealed craters 7 meters across and a ring of pulverized concrete. Sentinel-1 radar measured a surface sink of 0.8 meters, the mountain's skin buckling inward where the shockwave had traveled down the shaft. The numbers were not abstract. They matched the predicted collapse envelope from the DTRA target file, the same mesh refined over 15 years of counting and modeling. On June 24th, General Dan Kane addressed the Pentagon press corps. He spoke without flourish. The operation eliminated Iran's capacity to produce weapons-grade uranium at Fordow for an estimated 12 to 18 months. But the real proof came from the cockpit. Captain James Miller, B-2 pilot, described it as the brightest explosion I've ever seen, a cloud of dust that rose like a mushroom. The HUD confirmed all 12 weapons detonated as programmed. Overpressure, not heat or fragmentation, was the kill mechanism. The mountain, engineered to absorb impact, had been undone by a sequence of pressure waves timed to collapse its own geometry. $9 billion and 2 decades of engineering vanished in seconds. 12 bombs, each matched to a vent shaft, turned Fordow's defenses to rubble. Rafael Grossi, IAEA director, told the Security Council that preliminary remote sensing data indicates significant structural damage to the Fordow enrichment halls. Official timelines wavered, but the verdict was unanimous. Fordow was finished. Tehran's response was swift. Within 6 months, satellite images revealed a new excavation at Kuhi-Kolang Gazla, Pickaxe Mountain. Spoil piles climbed to 120,000 cubic meters, tracked by the same algorithms that once mapped Fordow. The new vault aimed for depths beyond 150 meters, a geometry designed to outrun any known weapon. March 2026 brought the Talagan 2 strike, a single bomb down a single shaft, and total collapse. The message was absorbed worldwide. North Korea, China, and Russia deepened their own vaults, layering concrete and steel. The mountain, once a shield, had become a test of calculation and nerve. In the end, the mountain's strength became its weakness. 6 sequenced GBU-57 bombs, each tuned to Fordow's 40 meters of granite, converted engineered sanctuary into engineered collapse. As IAEA inspectors confirm, almost all sensitive equipment is lost. The lesson is not that America built a bigger bomb, but a perfectly shaped answer to a 20-year riddle. In this calculus, geometry decides what survives and what vanishes overnight. Share your thoughts below.